Hello, welcome back to this video series on program synthesis using syntax guided synthesis techniques. Today I'm continuing to discuss about how we can synthesize non-trivial programs. For example, I would like to synthesize division by power of 2. For example, I would like the computer to give me a function f, right? The function f should take my input a can be any integer, and it's going to give me back a by 2, for example, or a by 2 power 2, or a by 2 power k in general, right? I wanted to be able to synthesize this. However, there is a restriction that I'm not allowed to use the division operator. Okay, so division is usually very slow. So if you divide something by something, you use normally division operator, and the division operator is many cycles slower than left shift, right shift, and addition, subtraction, that kind of operations. So the goal is to be able to come up with a division algorithm without using the division operator. That is the goal. Okay. So let me explain the idea first and take you through different stages. Okay. So what I'm going to do is I'll first assume a few things about a few things about k, just to get the idea across, and then I will generalize some of those. Okay. So my first part of the demo is to assume that a is greater than or equal to 0. Okay, that makes the explanation much more easier to start with. So I'm going to assume that my a is greater than or equal to 0. So in other words, we treat our a as an unsigned number. Okay, unsigned integer. Okay, unsigned is a data type. If you are familiar with the C programming language, you have two types of integers, unsigned and signed. The binary representation, unsigned means that the least significant, let me write it like this, for example. Here is the most significant bit, right? We call it MSB. The MSB is not treated as a signed bit, okay? That's the meaning of unsigned, okay? It's just, that's the meaning of unsigned. For the signed case, if there is 1 here, we will treat that as a negative number, okay? So negative, that I will come back later because I'm only going to talk about a greater than or equal to 0, okay? So what is the first step I'm going to show you? Yeah, I assume now k is equal to 1 to start with, and I'm going to ask the program synthesizer to come up with the program f for me. That's the part I'm going to show to you now. Okay, so with that brief background, let's get into the synthesis part, right? So what you're seeing here, let me first synthesize division by 2. That will be easier. Okay. Okay, I'm going to synthesize by 2 first, right? What I'm going to do though is that I'm putting a restriction on the type of elements I would like to see in the generated code or synthesis code, right? I would like to only see the operations that are listed as part of the grammar, right? The grammar says you're allowed to use add, XOR, and, or, negation operation, right? The minus, and then also you're allowed to use the bitwise not, shift left, logical shift right, arithmetic shift right. Okay, these are the operations that we allow. What kind of function are we trying to synthesize? We would like to synthesize a function called udiv2, right? That's the function that we would like to synthesize. That function better be equal to dividing a by 2. So that's basically the function that we would like to synthesize. Remember here, there is no division operation, right? This is the specification, if you like to call this a spec. Spec is what do you expect the program to do. The expectation is that if I send in an a, the program gives me a by 2. Okay, that's basically the expectation. So let's see whether we can synthesize a program but not using the division operation. So the program should not use division operation anywhere. Okay. Okay, so let's try this. I'm going to run this now for the case when we are dividing the input by 2. and it came back very quickly in a fraction of a second. The synthesized program is much easier to see now. Let me write it here for you. So it's basically, what is it? Your f of a is nothing but, what is this function? It's nothing but your a, this is basically right shift, right? Logical right shift by one position. Okay, so this is basically it. This means that if you send in, for example, a to be say 8, okay, the output of f of a will be 4, because what is the bit representation of 8? Let's take 8, right? 8 is 2 power 3, which means we need 4 bits to represent a, right? This is a in binary. Okay, what is the meaning of right shift by one position? It means, okay, I can just write it down here. It means your data moves one position to the right, bit by bit. So this 0 will be kicked out, so you'll have 100. And then, I mean, it's all binary. 100 doesn't make sense, but anyway, so you have a 0 in the front. This is basically the logical. I should put L here. Logical, okay? Although in the programming language like C, there is no such thing explicitly called logical. You use the same notation for logical and arithmetic shift. Okay. So this is what is this now? This is in base 2, right? Now, if you convert this into integer, what is this? This is base 2, which becomes 4, right? 2 power 0, 2 power 1, 2 power 2, which is 4. Okay, so as you can see, f of a is equal to 4. This is what the program is supposed to do. We are able to synthesize very quickly a program which matched our expectation. Okay, I have deliberately chosen my a to be greater than or equal to 0, right? Just to get the idea across first. So what we have achieved so far is that if we have a number a greater than or equal to 0, we can easily obtain an expression for dividing by 2 without using the division operator. Okay, now let's move on to the next part of the demo, in which I will show you how to synthesize, say, division by 4, for example. Okay, I'm just going to make it 4. I didn't parameterize it, just very simple code to play with a little bit. So I wanted to be able to divide by 4, right? So let's see what kind of program we can synthesize for this. Okay, so it's very quick. Again, very quick, right? And we can quickly write it as follows. The synthesized program is nothing but, what is f of a? Okay, is your a, right? This is this part. This is the definition part that it's synthesized for us, right? This is the input that we send in, and this is the output. It says, okay, what is output? It says a right shift, right? This R is right shift, by the way. This means logical. What is the binary representation we are having? B means binary. So 1 0 means 2. Okay, so we are right shifting something by 2 position. So if we now take a simple example, say a to be, now let's take something little bit complicated. Let's take a to be 9. Okay, so what is f of 9? We expect f of, oh, one moment. We are talking about division by 4, right? So what do we expect the answer to be? We expect the answer to be 9 by 4, which is 2, because we don't care about decimals in integer division. So let's write the binary representation of 9. 9 means 1 0 0 1, right? That's the binary representation of 9. Okay. And so what are we going to do? We are going to do a right shift of a by 2 positions, right? That's what we said here, which means the 0 1 at the right hand will go away. So we'll have the bit pattern like this. Okay, what is the value of this? This is nothing but 2. So this is exactly what the program should do, right? 9 by 4 is 2. So we found out that by doing right shift by 2 position, actually we are able to achieve division by 4. So we can now kind of generalize slowly, right? We did right shift by 1, we got division by 2. We did the right shift by 2, and we got division by 4. Let's continue this, see and whether we can observe some patterns very quickly. So What I'm going to do now is to go back to the program, right, and change it to, let's see whether we can do division by 8, right? What happens when you do division by 8? Okay, so 8 means in the bit pattern, now this x2 is hexadecimal x, okay? 8 requires 5 bits, right? Okay, because it's, one moment. 8 is 2 power 3, 4 bits, sorry. Okay. Yeah, so this should be, so we have 8, basically. We wanted to be able to divide by 8. This is the built-in bitwise division operation. We are saying take my x, which is in hex, by the way, therefore I don't have to do any conversion. I'm going to divide it by 8 and see whether we get the synthesized program division by 8. Okay, let's get out of this. And let's synthesize division by 8. Okay, so my program name is a little bit awkward, but anyway, it's division by 8. Okay, so what is this program doing? Let me walk you through this program. So the synthesized code looks like this now. Your f of a is equal to a right shift by, how much are you right shifting? This is a right shift by 3. Okay, so we saw the pattern earlier. When we right shift by 1, we are actually dividing it by 2. When we right shift by 2, we are actually dividing it by 4. So this pattern is emerging slowly. When we did a right shift by 1, we were actually dividing it by 2. When we did right shift by 2, we were dividing it by 2 square. And when we did just now right shift by 3, we think this is 2 power 3, right? Let's confirm with an example. Let's take our a to be say 10, right? What do we expect the answer to be? F of a means 10 divided by 8, which is 1. So what is bit pattern of a? 10 means 8 plus 2, right? This is the binary representation. And we now remove the last 3 these 3 bits due to the right shift. What we are ending up is 0 0 0 1, right? Which is nothing but 1. Okay, that's exactly what we got as the answer, right? When you divide 10 by 8, the answer should be 1, and we got this. Okay, so you can actually play with this a little bit more, and you can confirm that unsigned numbers, when you right shift by k position, actually, if you have a number a and if you right shift by k position, right, what you are actually doing is you're taking the number a and dividing it by 2 power k. That's basically what you're doing. This is the general formula, right? When k is equal to 1, this is the fact, k is 2, this and this. Okay, so to sum up, what you have seen so far is how to synthesize a division function, right, without using the division operator. Okay, that's the first part of this demo. In the next part, I will show you how to synthesize division of unsigned numbers, which are much more trickier. Okay, thank you very much.